Hi guys, welcome back to the channel. In the last lecture, we have discussed about the plastic analysis theory, okay? And we also discussed what are the advantages if we design our structure according to as per the plastic analysis theory over the elastic theory, okay? We made some conclusions over there, right? And we also discussed that in plastic analysis, each fiber the fiber in each cross section will yield, and it will give a moment which we call the plastic moment. Okay, so when let us suppose in this beam, simply supported beam, if we apply a load W at the center, okay, and at this cross section, we assume that this cross section, if we draw the stress diagram, if this is B and this is D, right? If we draw the stress diagram over here, then we came to the conclusion that each fiber will yield, okay, and the stress at each level will be sigma y. This thing we have discussed in the last lecture, okay, and this behavior we called it as plastic behavior, right? So now in actual scenario, this will not be case, okay? There will be some elastic core present in this cross section, okay? So what I meant by that is that in actual scenario, there will be always some elastic portion in the cross section, okay? So basically you can see from this stress diagram, this is our elastic portion. This portion is our elastic portion, okay? The stress will be sigma y over here because we are considering the rectangular cross section, okay? And it is symmetrical about both the axes. So at this point the stress will be sigma y, right? So this will be the actual case. So this will be the actual case, right, where we will be having some elastic portion in the cross section, okay? So this is basically the elastic core. But in our analysis, we generally neglect this depth is basically the depth of the cross section is h. Okay, in our analysis, we assumed this stress diagram, okay, to make our analysis little bit simpler, okay. But let us suppose if you get the plastic moment from this diagram, let us suppose is MP1, okay, and from this the plastic bending moment will be MP2, right? Always remember that MP2 will be greater than MP1, okay, right? This moment will always be greater than MP1, right? So if you see that we are assuming this is our actual case. In actual case, our moment of resistance, this is nothing but this is moment of resistance, okay. Moment of resistance is less for this diagram as compared to this diagram, but we are assuming this stress behavior in which the moment of resistance is greater than this MP1. This MP2 is greater than this MP1. So generally, if we made some assumption, we will try to be in safe side, okay. But here you can see that this MP2 is greater than MP1, so we are not little bit unsafe side, okay. But this thing will be balanced by that thing where we have assumed we are neglecting the strain hardening, okay. So this thing basically will be balanced by strain hardening because we neglected the strain hardening effect, okay, right? So in actual case, the strain hardening effect will be there and this effect will be there, okay. So combination of these two will give us this stress diagram basically, okay. The moment of resistance will be this strain hardening will balance the moment which is less for this actual scenario, okay, because we are neglecting the strain hardening effect, right? So this is the actual plastic behavior, okay. And why we made this conclusion that there will be some elastic core in the cross section, okay. So in our analysis, we assume that strain distribution is linear, okay. Strain distribution is linear across the cross section, okay. So when the strain distribution is linear, so I'll draw the strain distribution over here, okay. So there will be, the strain distribution will look like this, okay. So at this point, let us suppose there will be some ultimate strain, you can say that EU, okay. Similarly, there will be ultimate strain, and this is tensile basically, and this is compression, okay. Now let us assume we will be having some elastic core at a distance y from this axis, okay. This is basically a neutral axis, okay. And if you apply the similar triangle concept in this strain diagram, and at this point, let us suppose the strain is epsilon, okay. So if you apply this, what you can say that if you apply the similar triangle concept, I can write, and this is basically h by 2, okay, or you can say that d by 2. So I can write EU over में d by 2 equals to E over में, but you can say that E over में y, okay, because we are assuming the linear strain distribution, okay. Now we want to calculate what is the depth of this elastic core, okay. So some part of this cross section will be under the elastic state, okay. So if you calculate y from this equation, y is nothing but it will be E into d by 2 over me EU, okay. Now if you want to achieve this, if you want to have if y is equals to 0, if there is no elastic part, in this cross section, for that y should be equals to 0, okay. For y should be equal to 0, EU should be infinity, okay, but that will not be the case, okay. Strain will never be the infinite strain, okay. Before that it will break, okay. But remember one thing, this EU will be much greater than this E strain, okay. This is, we are calculating at the ultimate point, and this is basically at yield point, okay. So as per this condition, our strain for this y to be 0, the ultimate strain should be infinite, okay. That won't be the case. So that's why we always have some elastic core within this cross section, okay. So this is the actual scenario in the plastic design, but we have assumed the stress distribution like this to make our calculation simple, okay. And one more thing, here we talk about this axis. We need to talk about this axis because this is very important term, right? So this axis is basically called the plastic neutral axis. The plastic neutral axis, right? So this is also called the plastic neutral axis. Okay, and remember one thing, in the plastic neutral axis is the term, the strain will be 0, the strain is equals to 0, and the stress should be equals to 0, okay. This we cannot tell from this stress diagram, okay. A point, if this is a neutral axis, okay, a point just above this neutral axis, there will be some compression, and below this neutral axis there will be some tension, okay. So at the neutral axis, the stress should be 0 and the strain should be 0, okay. And in case of this, when this whole cross section is yielded, this plastic neutral axis neutral axis is equals to equal area axis. Equal area axis. Why we call it as equal area axis? Because when we reach this stress, when we reach to this stress diagram, the compression force for the equilibrium of the cross section, for the equilibrium of the cross section, compression should be equal to tension. Okay, if we calculate the compression force for this portion, this portion, I can write sigma y into b into d by 2. Okay, or simple I can write sigma y into a1. Let us suppose this area is a1. Okay, and similarly all the fibers are reached to the sigma y state, right? And similarly for this case, for the tension part, I need to write sigma y is into a2. Okay, so sigma y will cancel out each other, so a1 equals to a2. So that's why this is called this plastic neutral axis is also called the elastic equal area axis. Okay, and this plastic neutral axis will be different from the elastic neutral axis. Okay, elastic neutral axis will always elastic neutral axis when the moment is less than my, less than equals to my, we are in the elastic state. Okay, in that case this axis will pass through the centroidal axis. Okay, if we have a cross section where we are having the double symmetry means in this rectangular case this is symmetrical about this axis and this is symmetrical about this axis. So elastic neutral axis will always coincide with the plastic neutral axis. Okay, so this is the case. So this will only happen when we will be having some double symmetry. Okay, so if we are having only single symmetry, let us suppose this is our cross section. In that case, this will be our neutral axis, elastic neutral axis, and this might be our plastic neutral axis. There will be some difference. Okay, so now I think you get some idea about what is plastic neutral axis and what is elastic neutral axis. Okay, in elastic neutral axis we calculate that neutral axis, the cross section is always under this elastic state. Okay, where the moment is less than the yield moment. But in plastic case, this whole the cross section has yielded and this section and the whole cross section is yielded. Okay, now we discussed about the term called the plastic moment. Okay, and what is this plastic moment basically? So plastic moment is basically what, if this is the stress diagram which we have assumed, all the fibers yielded, this is sigma y, right? So the net compression force from this portion will act, let us suppose, in this direction. Okay, net tensile force for this portion will act in this direction. Okay, so these two forces is forming a couple, and we are naming that couple is nothing but this couple is plastic moment. This couple moment is basically the plastic moment. Okay, because we are in the plastic state, we are calculating this moment of resistance in the plastic state. That's why we are calling it as a plastic moment. Okay, this is the maximum resistance capacity of the cross section. This is the maximum moment resisting capacity of the cross section. Okay, This is the maximum moment resistance capacity of the cross section. Okay, beyond if you increase a load, the section can resist maximum moment resistance up to the MP value. Okay, beyond that, at that point there will be some deflection or rotation, but there won't be any increase in moment. Okay, that thing we will discuss later when we will discuss about the plastic hinges, right? So this is the little bit idea about the what is plastic moment. Okay, and how this but you can say that in actual scenario what we are getting, what stress diagram we are getting over here. Okay, and strain distribution is always remember that thing. Okay, now next thing we will discuss about the moment curvature relationship. Okay, so moment curvature relationships. Next topic in this plastic analysis is moment curvature relationship. Okay, so in moment curvature relationship, basically these are helpful in calculating the deflection, the slope in the beam. Okay, so when the material is in elastic state, right? When the material is in elastic state, let us suppose this is the elastic state. As per the simple bending theory, which we have studied in this strength of materials, we have one relation, m over I equals to E over may R equals to F over may Y, right? So this is the relation which we studied in simple, but this is what the simple bending theory, right? And in this theory we assume that the major deflection is due to bending only. Deflection is due to bending. We are neglecting any shear deformation and axial deformation, right? So curvature will denote by K, small k. Okay, so curvature is nothing but it is inverse of the radius of curvature. It is inverse of the radius of this radius of curvature, basically. Okay, so what is this R basically? This R is this radius of curvature. Okay, and let us suppose if we have this simply supported beam. Okay, and this is bending like this if some load is acting on this, right? So if this is bent like this, and this is our neutral axis, this is what this will be elastic neutral axis. Okay, so so this radius is nothing. This radius will be the radius of curvature. Okay, this is basically the radius of curvature, and if you inverse that thing, we will get the curvature part. Okay, so if let us suppose this is this portion, this is what you can say that forming an angle theta at d theta at this O point, right? So this we have already studied in the simple bending theory. Okay, and this radius of curvature, this radius of curvature, if the radius of curvature is, let us suppose if this radius of curvature is infinite. Okay, so that means if this radius of curvature is infinite, that means this beam is having very high, infinite, or you can say that very large, very high bending stiffness. Okay, if your radius of curvature is very large, okay, then that means that beam is having very high bending stiffness. It is difficult to bend the beam. Okay, similarly, if curvature is less, if curvature is more, then the beam is having less bending stiffness. Okay, if your beam is if it has sufficient bending stiffness, then it is difficult to bend that beam. In that case, the radius of curvature will be more, and this curvature will be less. This curvature will be what you can say that if curvature, this radius, okay, if curvature is more, right, the beam is having less bending stiffness. Okay, if curvature is less, then we will come to this situation where R is very large. Okay, so now let us suppose at a distance from this y-axis, at a distance y from this neutral axis, at a distance of this y from this neutral axis, let us calculate the strain in this part. Okay, at the strain in this fiber which is at a distance y from this neutral axis. Okay, so at the neutral axis this is the zero strain axis. Basically, this axis will be nothing but r d theta. Okay, right, and at this point, at the fiber which is at a distance y from this neutral axis, I can write the value of the length of this axis is nothing but r minus y d theta, right? Now if you calculate this strain, okay, in actual case, if this beam is not bending, this if initial stage, this r d theta will be equals to the actual length of this fiber. Okay, this is the actual length of the fiber at neutral axis. Okay, so we need to calculate what you can say that we need to calculate what is the strain at the level y. Okay, so I can write r minus y, or you can say that the change in the length is r d theta minus r minus y d theta over my actual length is what, r d theta. Okay, when this beam is not loaded, the value of this length, the length of this arc will be equal to length of this arc when this beam is not loaded. Okay, so if you solve this thing, this is nothing but this is the strain. This strain is equals to y over me, okay, this theta, y over me r, right? And you can say that strain is equals to E over my y, this is K. So this is the relation, which we are getting. What you can say that this is a relation between this thing. What you can say, this is a relation between this radius of this curvature and this strain, and this strain. This is the relation between the curvature and this strain, basically. Okay, so if you want to calculate the curvature, you need to calculate the strain at that fiber which is at a distance y from this neutral axis. Okay, so now let us come to this plastic state. Okay, and this curvature basically you can calculate from here also. Okay, now if this is in elastic state, I can write this is sigma over में E, sigma over में capital E, okay, into में y equals to k. K is nothing but this R, right? So we can derive one relation sigma y equals to E over में R over में here and this M over में I. Okay. So this is the case for this, what you can say that this is the case for this elastic method, right? Now, this valid for this analysis is valid for basically, you can say that this is for the elastic, not this analysis, this value, sorry, if you want to replace this thing by stress, okay, this thing by stress, so you can write this will be equals to sigma over में E, sigma over में E into y equals to 1 over में R, and this is equals to k. So this is valid for this elastic analysis, okay, where our beam is bending and it is under elastic state. Okay, this relation is valid for both elastic and plastic state. Okay, because we are just using the geometrical property over here. Okay, and if you want to use this relation, that this relation is valid only for you can say that only for elastic analysis. Always remember that thing. Okay, the beam is bending and it is in elastic state. Okay, for that we can use this relation. Okay, this is easy. Now what happens when the beam is in elastic plastic state? At that time the problem occurs. Okay, so let us derive the relation between the moment and curvature when beam is in elastic plastic state. So when the beam is in elastic plastic state, let us suppose this is the cross section, right? And up to this portion is yielded. I am taking the rectangular case because the relation will depend, this moment curvature relationship will depend upon the cross section shape. Cross section shape. Okay. You need to calculate this for different cross section will have different moment curvature relationship, right? So first case I am taking the moment curvature for this rectangular case, right? And let us suppose this is E value, this is E. Okay, so this is our elastic core. This total distance is H and this is B. Okay. So if you look the stress diagram for this case, the stress diagram will look like this. Okay. Now, first we will calculate what will be the moment of resistance, for this case, right? For that, we need to find the moment of resistance for this state. So first I am considering this portion, these two portion I am taking. Okay. So we need to find one couple. Actually these two part, the net forces in these two part will form a couple. Okay, so first we will calculate, this is, let us suppose this is one part and this is one dash. Okay, we'll calculate the net force in this one and this one dash region. Okay, so for one this force will be sigma y into B into this distance will be h by 2 minus of E. This distance is h by 2 minus of E, right? So this is the cross section of the beam basically, and on that beam there is some stress diagram. Okay, if this is the cross section, the stress diagram the stress will act like this. Okay, don't confuse. Okay, the stress will be perpendicular to this cross section. Okay, if this is your beam, I'm talking about this cross section. Okay, and the stress diagram will be acting perpendicular to this cross section, right? So this is the case. This is the force. Okay, and this force will be, these two forces will be equal, and they are forming the couple, right? So this force will be acting at this point. Let us suppose this is F1, and this will be also be F1. So we need to have one lever arm. We need to find that lever arm. So this lever arm will be, this lever arm will be equals to H minus of this H by 2 minus E divided over my 2, and this will be into 2. Okay, this will be the value of lever arm. I am subtracting these two distances basically. This 2 multiplication is showing that I am subtracting these two distances, right? So if you solve this thing, you will be get H by 2 plus E, right? So this will be H by 2 plus E. Okay. Now let us come to this triangular part. This is the elastic region. Okay. So if you want to calculate again, what you can say that the moment of resistance. So I need to write half sigma y into B into E, and the lever arm will be, this will be 2E by 3 from this side and 2E by 3 from this side. So this will be 2E by 3 plus 2E by 3, right? So the value will be sigma y into B into H by 2 minus E, H by 2 plus E, plus sigma y to sigma y B E square over my 3. Okay, so this is the value of this moment when the material is in elastic plastic state, right? So again, if you solve this thing and rearrange the things, you will get this way, you get this value. Okay, so this is nothing but, this term is nothing but, this is our my. This is nothing but, this is our my. What I meant by that is only the extreme, this is for this case when your extreme fiber has just yielded. Okay, so the moment of resistance formula for that case is nothing but this my is equal to sigma y into bh square over my 6. This is the section modulus, this is elastic section modulus. Okay, this thing we have also, this thing you can see in the strength of material. This is basically the strength of material concept. Okay, so I'm directly calculating this value. This is my. Okay, so our relation is m equals to my 3 by 2 minus 2e square over my h square, right? So this is the case. Okay, so moment we have calculated, now we'll see what is the curvature basically. What will be the curvature? Okay, so in this case the curvature we have just calculated is the strain, this strain over my y. Okay, so basically through this formula we can say that the curvature is nothing but this phi value. Okay, this phi is, this is the strain at this y level. Okay, so this curvature is nothing but this phi, or you can say that equals to strain at this level is epsilon over my y. Okay, so here also the curvature will be this phi value, not in this case, we need to draw the strain diagram. So strain diagram will always be linear. So this is the phi for this case, for this stress diagram. Okay. So at this point, we'll be having some yield strain, and this is the E point, right? So I can write this K equals to, this small k is equals to Ey over me E. And remember that up to here, we will be having, this is elastic part. In this region, our relation that M over me Ei equals to 1 over me R equals to F over me Y will be valid only for these portions, because this portion is in elastic state, right? So this is the curvature. Okay. And let us suppose this is at this point, this is the elastic, this will be Ey, right? Okay. And let us suppose if we have this case, right, where this fiber is in sigma y, and this is the elastic part, elastic bending. When this top fiber has yielded, only the outermost fibers has yielded. Okay, from that, if you calculate this, what you can say that this curvature, that will be equals to epsilon y over me h by 2. Okay, so this is the case. Epsilon ky is this phi will be equals to, this is h by 2, epsilon y over me h by 2, right? And if you divide this thing, so this k over me ky will be equals to h over me 2e. Okay. So from here, E by h will be equals to ky over me k 2. Okay. So if you square this thing, this will be ky over me 4k square. Okay, and you need to put this value in this equation. Okay, so you get the relation m equals to my 3 by 2 minus of 2 into e square h square is nothing but this will be k square and this is nothing but this will be 4k square. Okay. So this is the relation which we are getting between this, what you can say that this curvature and moment relationship. Okay. Now, when we are in the elastic state, as per this formula, the moment is directly proportional to this k value. Okay. Beyond that, after crossing the elastic state, the relationship is not linear. Okay, relationship is not linear. We cannot use this formula. We will be having this type of relation over here. Okay. So now you can see that, now you can see over here, if you see this form, now you can see, we'll discuss that thing later. Now, this, let us suppose this is this M diagram, this is the moment and this is the curvature. Okay, so the up to the elastic part, the relationship is linear. Okay. Now, when this E value is 0, when E is 0, we will be having the plastic moment. Okay. So when your E is 0, when your E is basically 0, you can see that the curvature is basically tends to be infinite. Okay. So after that part, there will be some curve. So this is basically the ky up to the elastic part. And when E equals to 0, we are getting this MP value. Okay. When E will be 0, the curvature tends to be infinite. Okay. The curvature tends to be infinite. And the moment which we are getting is basically if you apply this thing, if you apply E equal to 0 in this equation, then you are getting this relation M equals to 3 by 2 of My. And this is nothing but this is MP value. This is the plastic moment. Okay. This thing we'll discuss later. Okay, so at this point, let us suppose this is the MP value. Okay, and after that, the MP value will be constant because moment cannot exceed this capacity, moment of resistance cannot exceed this capacity MP, and the curvature will increase. The curvature will increase without any increase in the MP value. And why this thing is happening, we have already discussed. Okay, so this is non-linear relationship. Okay, right? So this is the case, this is the thing I want to discuss with you guys. So now the purpose of this thing is basically we have one relation that curvature is basically, it is equals to, you can say that d square over my y over my dx square. Okay, this we get from this geometrical analysis. Okay, so this relation is valid for both, what you can say that both elastic and plastic method. Okay, so we need to find curvature and we will integrate those things to get the deflection and slope. Okay, so this is the way you calculate the what will be the curvature value basically. Okay, so you need to find the expression for the curvature, and then you need to integrate it to get the slope, and again you will integrate it to get the deflection, right? So in this way you will calculate the deflection or slope basically first you need to find the curvature relationship. Okay, that is the important thing. Okay, and how to do that we already learned over here, right? So guys, if you have any doubt regarding this, means how this moment curvature relationship, this relationship we derived, right? You can write in the comment section. Okay, I hope I made my point clear over here. Where this up to this portion is basically, this is the elastic portion. Okay, so you can use that linear relation between the what you can say that the moment and this curvature. Okay, but when we are in elastic plastic state like this case, okay, we cannot use that thing. Okay, so in the elastic plastic state you can see that the variation is non-linear, right? And up to this elastic state the variation is linear. Here this M is directly proportional to K, moment of curvature in this elastic state, right? So guys, if you have any doubt you can write in the comment section. So we'll meet in the next lecture. Okay guys, thank you very much.